Hello, everyone. My name is Hideki Tsuruta. I'm an engineer at IHI Corporation in Japan. So I will be talking about our research along with this outline. So first, introduction. So the application for CFRP materials is expanding, such as a fan in aero engines. The building block approach is used for the development of composite component. Sorry. This is a schematic image of BBA. So the top of highest levels, so the component and subcomponent test is high cost and high time consuming. So we need to reduce the test number of tests of component and subcomponent components. So by improving the accuracy of the analysis at lowest coupon test levels, the number of costly and time-consuming higher order tests can be reduced. By the way, the foreign object damage is an issue must be considered to ensure safety, especially impact resistance during bird strikes. This is a schematic image of coupon impact test. The projectile attacked the CFRP laminates in front of, in direction of out of plane. So the damage observed internal CFRP test specimen, such as the transverse crack and delamination. So the damage process of CFRP laminates due to out of plane loadings need to be investigated to validate the FM damage analysis method at the coupon test level. The many researchers have performed the X-ray microtomography in order to observe the fracture mechanism and fracture behavior. So we will suggest the combination of synchrotron, radiation CT technology, and compact material testing technology. So it's possible to observe the damage process of material in three-dimensional. So the purpose of our research is to validate the FM damage analysis method with quantitative data on CFRP damage under bending loads using X-ray microtomography. However, there is a technical challenge. This is a schematic image of 44-point bending fixture. We need to get a high resolution image. So we have to rotate the test structure by 90 degrees. So in this case, the X-ray are blocked by the test fixture. So we will suggest the method how to solve this technical challenge. So next, I will talk about experimental method. This slide shows the test materials and specimen shape. We have overlapped unidirectional CFRP pre-leg to create the CFRP laminates. So the lamination structure is shown here, which is 8 plies. Then we prepare the miniature CFRP specimen, depend on this design drawing. So right figure shows a photograph of CFRP specimen. The smallest section is the target of X-ray CT observation area. So I will show the static bending load test with using a compact testing machine and miniature specimen. Left figure shows a photograph of the compact material testing machine. So in this area, the specimen is fixed. The right figure shows the state of the specimen fixing area. The specimen was fixed in state offset by 5 millimeter from the axis center of testing machine, and by applying the axial load in direction of compressive. So by stepping motor in this here. So it was possible to apply static bending moment to the specimen. This slide shows the X-ray microtomography setup the compact test machine set on the sample stage unit. And this is a micro CT conditions. So finally, the voxel size of CT image is about 0.5 micrometer cubic. The scanning time is about 1 minute. So let's move on the experimental result. This slide shows the deformation of CFRP specimen under static bending load. Left figure shows the state of the specimen before loadings. So by applying the compressive load, so the specimen deformed in direction of out of plane here. So the specimen was successfully subjected to bending deformation by applying axial force. The right figure shows the load displacement curve under the static bending loads. The displacement was held, and X-ray CT observation was performed at the blue circle point. So totally 10 scans has performed. So next, this slide shows the in situ observation result of CFRP damage in 2D images. This figure shows the CT cross-sectional image in the specimen at load level number 5 to number 9 correspond to this load displacement curve. So first damage is the interfacial debonding in second layers, which is fiber direction is 90 degrees. Then interfacial debonding has grown into transverse crack, and the crack increased in the second layer. So finally, interlaminar delamination occurred between the first layer and second layers, so leading to final fracture. So now we have obtained the damage process of in these lamination structures. Next, I will talk about in situ observation result of 3D images. So right figure shows a 3D reconstruction image of the transverse crack and delamination at load level number 6 to number 9. So as we can see, the crack now only damage and voids are shown here. Sorry, and focus on the only first and second layers. So we have checked the we have checked the interaction between transverse crack and interlaminar delamination. This is a final result sheet. Left figure shows the quantitative data, so relationship between crack density, maximum crack length, and displacement normalized by fracture displacement. So please check, please see the blue colors. This is a crack density in the second layers. So the crack density is monotonically increased in second layer during the bending loads. So now we have obtained the quantitative data on crack density and maximum crack length for the first and second layers. So in the future works, quantitative data will be considered in the damage model of the FEM damage analysis. So I will talk my conclusion. This is my conclusion. So in situ observation of the damage process on one specimen under bending load was successfully performed using the compact material testing machine. the damage mechanism CFRP under bending load was found to be interfacial debonding of the carbon fiber, between fiber and resin interface at the 90-degree layers on the tensile side of bending, followed by formation of transverse crack due to their coalesce and subsequent delamination, leading to final rupture. So the quantitative determination of the crack density, maximum crack length were measured as a function of displacement normalized by rupture displacement. So thank you very much.